All right, good morning. So let's start with a very quick recap of what we did in the last class and see what we're going to do in this class. So in the last class, we spent a fair bit of time talking about sequences and limits. We formally defined what a sequence is, and then we distinguished between convergent and divergent sequences. And in particular, divergent sequences could either be oscillating or they could be unbounded, right? And we saw the notions of supremum and infimum of a set, and in particular, the supremum and infimum may or may not lie within the set itself. And if the supremum lies within the set, then we call it the maximum. If the infimum lies within the set, then it's the minimum. So the supremum and infimum of any real valued sets are well defined, whereas the maximum and the minimum may or may not be. Right? And we also define the limit of a sequence. So a sequence may or may not have a limit. If it converges, then it has a unique limit. If it does not, then there is no limit. But then we define two other notions, one the limit superior and the limit inferior, which I defined as follows. So the lim sup is basically the limit as n tends to infinity of the supremum over all m greater than or equal to n of f of m. And similarly, the lim inf is the limit as n tends to infinity of the infimum over all m greater than or equal to n of f of m. So these two quantities, the lim sup and the lim inf, essentially capture what happens for asymptotically large n. So in other words, the lim sup says that for really large n, most of the values of f of m are at most equal to the lim sup, and for asymptotically large n, all the values are at least equal to the lim inf. Right? And if the lim sup is equal to the lim inf, then it's equal to the limit. We say that the limit exists. So a necessary and sufficient condition for a sequence to be convergent is that the lim inf should be equal to the lim sup. All right. So in some cases, it's easy to identify what the lim sup and the lim inf are. But on the other hand, so sometimes it may not be a little more complicated. All right, and you should, if you've not already done so, you should try to prove the following yourself, that every increasing sequence which is bounded from above always has a limit, and every decreasing sequence bounded from below has a limit. And this gives the following result, that every bounded sequence has a lim sup and a limit. Yes. Yes. No.
In lim sup and lim inf, so if that means if n tends to infinity, that function value is at the, like for lim sup it is at the most that one, like lim sup.
Yes, so it's at most, so it cannot be any greater than that. So for asymptotically large n, it's going to be close to the lim sup, but not much larger than the lim sup.
That means at the most, the function value should be at the most lim sup.
Yes.
Okay. Okay.
So for example, if you take the sequence -1 raised to the n, right? So the lim sup is equal to +1, and the lim inf is equal to -1.
Yeah.
All right, and in particular, so I'll make some more comments regarding this in about a minute. But before we proceed, are there any other questions regarding the topics that we discussed in the last class? Any questions at all? All right, so we'll wrap up our discussion on sequences in this class, and then we'll go on to another important topic, which is convexity. In particular, we'll see that the set of all achievable rates for any multi-user system, it always forms a convex set. And in showing so, we'll discover a very important technique, which is sort of the equivalent of or a generalization of the time division multiple access technique that we saw in the first class. All right, so let's move on. Yeah. So you should really try to prove the following on your own. And if you have an argument, just post it on Piazza, and and then use this to show that every bounded sequence has a lim sup and a limit. So maybe I'll give maybe a couple of hints to show this. So let us consider the following. So let's say that I have a sequence an, right, and I'll define Bn to be the supremum over all m greater than or equal to n of an. Right? So therefore, Bn plus 1 is equal to the supremum over all m which is greater than or equal to n of n plus 1 of am, right? So basically this is a set. So the set of all m greater than so the set of all am for m greater than or equal to n is an infinite set, and you're taking the supremum over that set. Okay. So what can you comment about Bn and Bn plus 1? Can you say that one is greater than the other or less than the other, or are they equal? Anyone? Okay, so Shantanu guesses that they're equal. Anyone else? So let's look at the two sets. Okay. So you have the set of all, you have one set which is am for m which is greater than or equal to n, and then you have another set which is the set of all am which is for all m greater than or equal to n plus 1. Now what can you comment about these two sets? Is one larger than the other?
So Bn is at the most Bn plus 1.
Correct. So right. So we show that. So this set, the first set over here, this contains the second set, right? Because this is the set of all am for m greater than or equal to n, whereas this is the set of all am for m greater than or equal to n plus 1. So this contains one more element than this set, correct? And here you're taking the supremum over a larger set, whereas here you're taking the supremum over a smaller set, right? So, and if you take the supremum over a strictly larger set, then the supremum can only be larger, right? Because you have more elements and potentially the supremum could be larger. So the supremum over the second set is obviously going to be less than or equal to the supremum over the bigger set, right? So therefore you have Bn greater than or equal to Bn plus 1, as both Chandramouli and Suman guessed, right? So, okay. So therefore, what can we conclude? So the lim sup is, what kind of a sequence is it? It's a non-increasing sequence, right? So it's a decreasing sequence. Sorry, not an. So the sequence Bn is a decreasing sequence. So Bn n greater than or equal to 1 is non-increasing. Right? And if the sequence is bounded, then obviously if an is bounded from above and below, then bn is also bounded from below. So it's a non-increasing sequence which is bounded from below, and therefore this statement over here implies that the lim sup always exists. So similarly, you can make an argument about the lim sup. So you'll see that if you define Bn as the infimum over all m greater than or equal to n of am, then this is a non-decreasing sequence, and if it is bounded, then the lim sup, then the lim inf always exists. All right. So maybe just look. Let's take a quick example and then move on. All right. So let's look at minus one raised to n. Okay. So an is minus 1 raised to n. What is bn for this? So if I define bn in the following manner, where bn is the supremum over all m greater than or equal to n of am, then what is bn equal to?
One.
Right. So it's equal to 1 for all n. Right. So similarly, if I define Cn as the infimum over all m greater than or equal to n of am, then this is equal to,
Minus 1.
it's equal to minus 1, right? So clearly in this case, so Bn is a constant sequence, Cn is a constant sequence, and both of them have limits. Right. So one very important property that we'll be using later on is that is the following property of lim sup and lim inf. So if you have a sequence where a plus is the lim sup of the sequence and a minus is the lim inf of the sequence, then there is a subsequence of the sequence. So basically you can find n1, n2, n3, and so on, all the way up to infinity, such that the sequence, the subsequence ani, I greater than or equal to 1. So this is a convergent sequence and it converges to the lim sup. And similarly, there is another subsequence, there is a different sequence, let's maybe call it bn, such that, sorry, this is a subsequence of an, let's call it bni, which converges to the lim inf. Okay, so in this particular example over here, the subsequence which converges to the lim sup is basically all the even indexed sequences. Right, the even indexed subsequence converges to +1. All the odd indexed subsequence converges to -1. Right? And this holds in general for any sequence. There's a subsequence which converges to the lim sup, and there's another subsequence which converges to the lim inf. All right. So in trying to answer, so there are a couple of other concepts which are equally important, and one is the notion. One is the different notions of infinities. So you may have seen this. Some of you may have seen this in some other course, but in case you haven't, then this is a useful concept to know. So in particular, if you look at the following sets, you have the set of integers, which you know is infinite, and you also have the set of real numbers, which is also infinite. But in some sense, these two are not the same set, right? In some sense, the set of real numbers is actually much, much larger than the set of integers. Right? And you also have the set of rational numbers, which intuitively it feels that this should lie somewhere in between the set of integers and the set of real numbers. Right? So there are different notions of infinity. And in particular, so if you look at the sets Z, Q, it's clear that the set of real numbers is obviously a superset of these two, and therefore it should be much larger than these two. But even if you look at the interval 0 to 1, right, this is an infinite set. It contains infinitely many points. It is not a subset. It is not a superset of either z or q, but in some sense it is still larger than the set of integers, right? And the way to formalize it is the following. So we'll say that a set, any subset of the reals, or any set, is countable if you can define a one-to-one mapping from the set to the set of integers. And the set of the all finite sets are countable by this definition, and both the set of integers and the set of natural numbers are countable. But what is slightly less obvious is that the set of all pairs of integers, or the set of all n tuples of integers, are also countable. In some sense, they have the same size as the set of integers. And even more surprisingly, the set of rational numbers is countable, because you can write any rational number as p over q, where p is an integer and q is an integer, and therefore if z square is countable, then the set of rational numbers is also countable. Okay, I don't want to spend too much time on this, so you can go through the notes after the class. And in particular, here's a proof of the statement that a set of rational numbers is countable. So it's an interesting proof. I encourage you to go through this. But in any case, it's good to know about this. Right? And similarly, if you cannot find a one-to-one map from the set A to the set of integers, then we say that the set is uncountable. Right? For example, the set of real numbers, the set of all real vectors, a set of all complex numbers, and any interval, or the set of irrational numbers, all of these are uncountable sets. And these are much larger than the set of integers. So sometimes you'll see that the set of integers, or the set of natural numbers, these are countably infinite sets. All finite sets are countable but finite, whereas all these sets over here are uncountably infinite. All right. So just keep this in mind. But coming to the point, so what kind of statements do we want to make in information theory? Right? So one class of statements that we want to make is sort of the following. So let us now consider, let us now look at a formal statement of the channel coding theorem. Right? These are the sort of results that we want to show, and see what they imply. All right, so the channel coding theorem, formally stated, says the following. So suppose you have a discrete memoryless channel, py given x. So these are the channel transition probabilities, and let C be the maximum over the mutual information with respect to Px of, all right, so C is max over all Px of the mutual information between x and y. Then Shannon's channel coding theorem says the following. So it says that you can find, so if you fix any epsilon greater than 0, so you back off from this capacity by any small amount, then there exists a sequence of encoders and decoders. Basically, for each block length, you can find an encoder and a decoder. So an encoder is a map. So an encoder takes kn bits and outputs a sequence of length n. The decoder takes the received sequence and outputs kn bits. And these sequence of encoders and decoders satisfy the following. So the lim sup, as n tends to infinity, of the rate is greater than or equal to c minus epsilon, and the lim sup of the probability of error is equal to 0. All right. So basically, for each n, you can construct a code such that there is some subsequence of codes which converges to a rate greater than converges to a rate epsilon close to capacity, and the probability of error is vanishing in n. So it's okay if you cannot construct a code for every n, but as long as there is a subsequence of codes which gives you a rate greater than or equal to the c minus epsilon, and the probability of error is vanishing, we're happy. All right. So any questions so far?
Sir.
Yes.
Sir, can you elaborate it? I am not able to understand.
All right. So ultimately, our goal is to find out what kind of codes you can construct, right? You want to design an encoder and decoder for which the rate is as large as possible and the probability of error is as small as possible, right? So obviously, if you fix an n, so you can communicate in n channel uses. So the setting is the following: you have a message of which consists of k bits, which needs to be encoded and transmitted across a channel. The channel is described by the channel transition probabilities. So think of this channel as maybe an additive white Gaussian noise channel, or maybe a fading channel, right? So you transmit n symbols or a sequence of n symbols, and this is corrupted by noise, and then you receive the noisy version of the symbol of the sequence, and you have a decoder which outputs an estimate, right? So one question that you can ask is, okay, you fix an n, what is the largest, what is the minimum probability of error that you can achieve? Right, let me just write down. Yep, so this is the problem. We want to design this encoder and decoder such that the rate is as large as possible, with the rate being defined as kn by n, and we want to ensure that the probability of error, so the probability that m hat is not equal to m, is as small as possible, right? And if we want to do so, it is much harder to say what the best encoder and decoder is for a given n. So the only statements that we can concretely make is what we can say about really large n. And basically what Shannon proved in his work on source coding and channel coding is that you can construct a sequence of codes such that asymptotically the rate of the code is close to capacity, and asymptotically the probability of error is vanishing in n. So it's possible that for some n the probability of error is large. You don't know how to design a good code, but then it is still possible that for really large n, so for really large delays, the probability of error can be made as small as you want. Right? Is that clear?
Hello, sir.
Yes, Suma.
So, in the first statement, that lim sup as at n tend to infinity kn by n is at least c by epsilon. So it
Yes.
should be obviously that should be at the most c, right? Lim sup tend to
Correct.
infinity
So,
kn by n. It cannot go beyond c, right?
exactly, it cannot go beyond C because the converse of the channel coding theorem says that it cannot go above C.
But it
But
is
you can
forced.
always make sure that it's above C minus epsilon.
Okay. So that means like it is an epsilon gap between capacity.
Correct. So for every epsilon, so no matter how small an epsilon you can choose, it is possible to find a sequence of code such that the lim sup is at least C minus epsilon.
So in that statement, it seems like if epsilon equal to 0, then it is at least c. But like
So that's what, right? I'm saying that for every epsilon strictly greater than 0.
yeah, yeah, yeah. Yeah.
Right? I'm not saying that for that the lim sup is greater than or equal to C.
Okay.
All right. So the channel coding theorem also says that the lim sup of Kn over n is at most C. It's actually at most C plus epsilon for every epsilon greater than 0. Or the probability of error will be bounded from below by epsilon.
Sir, what does this Kn implies, sir? Is it a
So, so,
sequence?
so yeah, so for each n, all right, so Kn is basically a sequence which says how many bits of information you are transmitting in n channel uses, right? So in particular, I'm using this subscript n to indicate that it can be a function of n. Maybe for 10 channel users, I'll transmit 3 bits. For 11 channel users, I'll transmit 4 bits. Maybe for 100 channel users, I'll transmit 35 bits. All right. But what I'm interested in is how many information bits I can transmit for a really large number of channel users. For really large n.
Sir, is there a rule that it should be converging?
So that is what. So Kn
Kn.
need not converge. So that's the point here, that Kn need not converge. But then we know that the lim sup of every sequence exists, right? So that is why we are using the statement here. The statement here is that the lim sup is greater than or equal to C minus epsilon. I'm not saying that the limit is greater than or equal to C minus epsilon. Any other questions? All right. Okay, so here's some more reading. So frequently when we're trying to do some derivations, it's useful to know some of this notation, which is also very commonly used in information theory and more so in computer science. It is this big O notation. So I won't discuss it now. You can just go through it after the class. You can, for example, you can see the Wikipedia page on the big O notation. It's sometimes also called the Bachmann-Landau notation. And this basically describes, this is notation to describe how two sequences behave with respect to each other, whether one sequence is much larger than the other, or it behaves roughly as some other sequence. Okay, and we'll use a notation like, for example, f of n equal to little o of 1 or big O of 1 theta of 1 or maybe little o of 1 over n and so on. Okay, so just go through this, and it's a good idea to know what these terms mean, because it sets up the terminology which is used both in this class and also whenever you read any textbook or works on algorithms or computer science. All right. With this, let's move to a different topic, which is convex sets and convex functions, right? Because we'll be using a lot of this. Right? So frequently, whenever we talk about rate regions or properties of channels, we'll be interested in properties of sets, and it's useful to have a good understanding of what some of these terms mean and what properties they have. Right? So in particular, here is some more notation. So given any vector in Rn, I'll define the neighborhood. So B epsilon of x, this is again new notation. This is basically the n-dimensional ball of radius epsilon and center at x. All right. So formal definition of an open set is that for every point within the set, you can find a small neighborhood which lies within the set. So for example, let us take the set 0, 1. Okay, so we know that this is an open set, and in particular, this means that no matter which point you take within the set, so you can take 0.99999, I can find a neighborhood, a small ball around this point, such that it lies within this set. All right, because I can always take a ball of radius 0.0000001. So 0.999999 plus 0.0000001 lies within this set. Right? Every point within that lies within the set. So if I draw a picture, this is an open set. So no matter which point you choose, I can always find a ball of radius. I can always find a neighborhood of points which lies strictly within the set. So you can never, so basically there is no edge for this set. Right? So that's what it intuitively means. And open sets are sometimes not very nice, and we sometimes prefer closed sets. So we'll say, so one way of defining what a closed set is that if the complement of the set is open, then we say that it is closed. And another way of defining it is using what are called limit points. So a limit point is basically any point in Rn which is epsilon close to every point in A. Right. So again, I don't want to spend too much time on open sets and closed sets. You can go through the notes. These will be uploaded on Piazza, but basically, so sets of the form open interval 0, 1 are open. Sets of the form closed interval 0, 1 are closed. But it's possible that not every set is closed or open. So for example, the set open at 0 and closed at 1. So this is a set which is neither closed nor open. And the set of all real numbers, this is a set which is both closed and open. So these are not, what do you say? So a set can be neither, so a set can be open, it can be closed, it can be both closed and open, and it could be neither closed nor open. Right? So this is just useful information. But what we are really interested in are convex sets. All right. So a convex set is basically one where if you take any 2 points in the set, so you have some set, it's convex if you take any 2 points in the set and look at the straight line joining the two, the entire straight line lies within the set. All right. So basically, if you take any point x and any point y, then alpha x plus 1 minus alpha y for alpha between 0 and 1 lies on the straight line joining x and y. Right? So a set is convex if between every 2 points, the line joining between these 2 points also lies within the set. So this example that I have drawn over here is not convex because I can consider a point over here, I can consider a point over here, and I can draw a straight line between these two, and it lies outside the set. All right, but sets of this form, these are convex. All right, so this is an example of a convex set. All right, so any questions regarding the definition of a convex set? All right, so let's go to the important result that we want to show in this class, and that is that. So okay, sorry, not here. Yeah. All right. So let's consider any multi-user system. Okay, suppose that you have some kind of a multi-user system where you have L transmitters and L receivers. So the L transmitters have messages M1, M2 up to ML, and they want to communicate these to L receivers so that the receiver I wants to decode the ith message. Okay, and these are connected using some complicated channel, which is described by some channel transition probabilities. All right, and we want to know what kind of rates can be achieved over such systems. So one simple example. So in general, you could combine two receivers. I mean, so maybe one receiver wants to recover multiple messages or maybe one message. So this can be generalized quite a bit. All right, but let's just consider, you can consider an even simple problem of where you have, say, one transmitter or two transmitters which communicate through some channel to, let's say, two receivers. All right, and they want to decode the messages of the two transmitters. Okay, and we want to know what rates can be achieved using over such channels. All right, so what kind of codes can we design, and how do we design these codes? All right, so we'll say that some set of rates are achievable. So you look at any real numbers, say 0.1 and 0.2. We'll say that a rate pair or a rate tuple is achievable if you can construct encoders and decoders such that asymptotically the rate is equal to Ri, and asymptotically the probability of error is vanishing in n. All right, and we want to know what kind of rates are achievable. All right, so let me just maybe repeat. So our goal is to understand what kind of rates can be achieved, what kind of encoders and decoders, what kind of channel codes we can construct for multi-user systems. Okay, so in general we can have L transmitters and maybe K receivers, but in this example I have L transmitters and L receivers, and each transmitter wants to send the ith transmitter wants to send a message to the ith receiver. Okay, so basically transmitter I has k I bits to transmit, AI bits to transmit to the ith receiver, and all of them encode their information bits or message bits into vectors of length n. So n is the same for all transmitters and all receivers. So transmitter I encodes ki information bits to n codeword symbols. So basically you're using n time slots to communicate across the channel. So all of them communicate simultaneously across this particular channel. So k bits are encoded into n message symbols or n encoded symbols and transmitted across the channel. Each receiver gets n received symbols, and the relationship between yn of I and all the xn's could be something complicated, but it is in general described by some transition probability. Let's not worry about that for now. And the goal is to decode the k transmitted bits. Right? So this is k of I bits need to be recovered at the receiver. Okay, and we'll define, and our goal is to understand how k of I divided by n behaves asymptotically. Right, so this is the asymptotic rate that is achievable is denoted by Ri. So Ri is the rate at which the ith transmitter can reliably communicate across the channel to the ith receiver. Okay, is this setup clear? Okay, so we'll say that some rate tuple is achievable if you can construct encoders and decoders for which kn of I over n is close to Ri or asymptotically equal to Ri, and the asymptotic probability of error of decoding the ith message is vanishing. All right, and the rate region is basically the set of all achievable rate tuples. And in general, this is going to be some set. So the question that we want to address is, let us look at the set of all achievable rate tuples. All right, R1, R2. So what can this set look like? Can it look something like this? Or can it look something like this? And the claim is that it cannot. It should always be a convex set. And we'll see why that is the case. And in doing so, we'll see an important technique. which as I mentioned, generalizes time division multiple access. All right. So let's just to understand, make sure that we're all on the same page. Let's try to see what a rate region would look like. So suppose you have a single transmitter and a single receiver. All right. So basically, the set of all achievable rates is a subset of the real line. So you have only R1, and you have a channel Py given X. All right. So what does the rate region look like for single transmitter and single receiver? Yes, anyone? So what does the channel coding theorem say?
So it says that the achievable rate is if intensity infinity is at least c minus epsilon,
Correct.
and the probability of error is it goes to zero.
Correct. So in other words, if we go by this definition, so we say that a rate is achievable if asymptotically the probability of error is vanishing, and Kn over n is equal, it converges to Ri. Right? Or the lim sup is equal to Ri. So from Shannon's channel coding theorem, we know that any rate less than C is achievable. Right? So if I mark this as C in the real line, then basically the rate region is basically, what is this? It's an interval, right? So for single transmitter and single receiver, the rate region is basically a closed interval from 0 to C. All right. Any questions? So similarly, for let's say for a two-user Gaussian channel, a two-user Gaussian multiple access channel that we saw in the very first class, the rate region looks something like this. It looks like a pentagon. R1, R2. This point is half log 1 plus P over sigma square. This point is also half log 1 plus P over sigma square. This point was half log 1 plus P over P plus sigma square. So the same for this particular point. And this particular point is convex. Oh, sorry, this set, the set of all achievable rate regions is basically the region enclosed by this pentagon. Is basically this entire region over here, and this forms a convex set. Okay. All right. So the claim is that every rate region is convex. So no matter what kind of a channel you have in between the transmitters and the receivers, irrespective of whether it's a multiple access channel or a broadcast channel or any such complicated channel, or at least for a general class of channels, the set of all achievable rate tuples always forms a convex set. Okay, so all right, so you take any region, this forms the rate regions form a convex set. Okay, so if I want to prove such a statement, what do I have to show? Okay, so before that, Chandramouli has a more basic question about the problem. Why do different transmitters have different case when all messages are from the same source? So the point here is that the messages are different. All right. So you have two transmitters. So for example, think of it think of the following problem where you have two different cell phones which are trying to communicate to a single base station, right? Maybe the channel from maybe the first cell phone is closer to the base station than the second cell phone. So obviously there is more noise from the second cell phone to the base station than the first cell phone. And so in N channel uses, the first cell phone can transmit more information bits to the base station than the second one, right? And therefore, maybe in N channel uses, the first cell phone will transmit k of 1 bits to the base station. The second one will send k of 2 bits to the base station, where k of 1 could be greater than, strictly larger than k of 2. Okay, so is the setup clear?
Sir, which means the K is not constant all over the time.
No, so there are different case. It's the
Yes.
point that I'm trying to make. So k is a function of n, but also is a function of the user, right? So it's really kn of I, right? So for each n, transmitter 1 sends kn of 1 bits, transmitters 2 sends kn of 2 bits, and so on.
ওইখান থেকে জল সব
Right?
পড়েছে এই জল দাঁড়িয়ে আছে
Suman, could you please mute yourself?
হ্যাঁ তাহলে এইভাবে চলবে
Right. So hopefully the setup is clear.
Yes, sir.
Okay, great. So now we want to show that the rate region is convex. So what does it mean? What do we want to show? So basically what we want to see. So one way to prove this is to use the definition of convexity, right? So basically if some rate pair, let's call it R1, R2, is achievable. So basically it means that we can construct codes or sequences of codes for which the asymptotic rate is R1. For user 1, the asymptotic rate is R1. For user 2, the asymptotic rate is R2. And maybe there's some other rate pair, which is R1, let's call it R1 prime, R2 prime. So asymptotically, for large enough n, the rate for user 1 is close to R1 prime, and for user 2 it is close to R2 prime. Then we need to show that any rate pair which is along the line joining the two can be achieved. Right? So suppose that R1, R2 and R1 prime, R2 prime are achievable. Okay, so to show that this is convex, all we need to show is that the straight line joining the two is achievable. So you take any alpha between 0 and 1. We want to show that R1 alpha R1 plus 1 minus alpha R1 prime, comma alpha R2 plus 1 minus alpha R2 prime, this rate pair is achievable. All right. So any suggestions as to how we can prove this? So the basic idea is the following. So there is some coding scheme which achieves a rate R1, R2. And there is some other coding scheme which achieves a rate R1 prime, R2 prime. Now my goal is that given these two coding schemes, I want to design another coding scheme which achieves a rate alpha R1 plus 1 minus alpha R1 prime, alpha R2 plus 1 minus alpha R2 prime. And one way to do this is the following. So for alpha fraction of the time, I will use the coding scheme which gets me to R1, R2. And for 1 minus alpha fraction of the time, I will use the scheme that gets me a rate R1 prime plus R1 prime, R2 prime. So the rate that I can achieve would be alpha R1 plus 1 minus alpha R1 prime for the first user, and alpha R2 plus 1 minus alpha R2 prime for the second user. Right? So you should think about this a little more carefully. And so we can continue this in the next class. But if there are any questions, then I can address them. So any questions?